In this video, I want to talk about what does it mean for an object to be charged, as well as talk a bit more about Coulomb's law and start digging into the weeds a bit with Coulomb's law. But first, we need to know what it means for an object to be charged in order to answer that question. So, when we start talking about charged objects, it's really sort of important to understand something that you saw in the videos where they were explaining the history of it. Before they understood what was happening at the atomic level, there was a notion that something was being exchanged or moved around in these processes where things got charged. You saw that there was they imagined sort of almost an electrical fluid going back and forth between different things. But a couple of notions in that. Obviously, that's not true, but it was a good enough guess for the moment. The other thing is that nature was seeking an overall equilibrium, which is what was causing things to flow back and forth unless forced to do otherwise. We're going to dig down now into a more modern understanding of what this is. But remember, all these scientists did all this really great work before they knew what was happening at the atomic level. So let's dig down to that atomic level to really talk about what it means to be charged. So, what does it mean to be charged? All right. So first off, charge is a basic quantity of nature. So charge, here we go. Symbol for charge is going to be lowercase letter q. Why? We're running out of letters, so just go with it. And the unit for charge is going to be something called the coulomb, right? Which we use just capital C, not lowercase c, capital C, in order to denote. Now, it must be said that we started quantifying coulombs of charge back in the early 1800s, before they even knew what was going on. They had no sense that what was actually happening was so ridiculously tiny, because we're going to find 1 coulomb of charge is an enormous amount of charge. So that's going to become important in a couple of minutes. Now, flashing forward, we know that charge has to do with some certain subatomic particles. So if I asked you, well, what is those subatomic particles? Well, obviously we're talking about the electron, we're talking about the proton, we're talking about the neutron. Okay, so there we go. Just a little bit of symbolic work there. The symbol for an electron here, if I was trying to say like 1 electron, a shorthand is I might go 1 e, lowercase e, with a negative sign there as a superscript. 1 proton might go 1 p with a plus. Now there's another sign there as well. I'm just going to put that out there. It's 1 h plus. And we'll talk about why that is true a little bit later. And the neutron, 1 n0, or in another notation, 1 0 n. Okay? So those are just some notations that we might be using as time goes along. But also give you a flavor of history. When were these things discovered? Well, the electron is not discovered until 1897. Anyone know who in 1897 discovered the electron? Well, the person is our friend J.J. Thomson. Now, you may know J.J. Thomson of the famed plum pudding model, right? Hopefully you've heard about that, the plum pudding model. This was in that time period we're looking about the structure of matter, and he envisioned that matter was continuous. And the continuous part of matter was positive, and then there were electrons embedded within that continuous thing. So they were like the plums in a plum pudding, where the positive part was the custard and the negative part was the electron, the plums suspended in the pudding. So the overall matter was neutral, because we know that neutral overall is the general state of things. And it wasn't until actually 1919, well, really 1917 he's doing the work, but 1919 he's publishing. A guy by the name of Rutherford discovers the proton. Now you might know Rutherford's name in another context, Rutherford's famous gold foil experiment, right? That experiment was done in published in 1911, and in that he publishes the existence of the nucleus. He discovers the nucleus and knows that the nucleus is positive, right? It's not until 1919 that he finds out that the positive part of the nucleus is indeed this proton. And it's actually not until 1932 that a gentleman named James Chadwick figures out or discovers the neutron. The neutron is so hard to discover because it's not charged. And these guys were using the properties of charges in Coulomb's law, actually, and other things, magnetism, in order to figure out something about these things. And obviously, neutrons would not respond to any of that. Anyway, so that's some basic information about historically, right? So we discovered these things in the early 20th century, and we still don't really understand them. We just know that these things exist. We understand them a lot better now, but this is all fairly new science. Now, when we're talking about the properties of them or information about them, let's go down. An electron, again, a proton, and a neutron. Normally I would do this in one big table, but I don't want to squeeze. How about mass? The mass of an electron, it's really, really, really tiny. 9.11 times 10 to the negative 31st kilograms, right? Thomson discovers the electron in 1897, but we don't find the mass of an electron for another 14 years. And another experiment that we'll talk about later, something called the Millikan oil drop experiment. But that is really, really, really tiny. 10 to the negative 31st kilograms. Really, really, really tiny. The mass of a proton, larger than that, 1.67 times 10 to the negative 27th kilograms. And the neutron, 1.67 times 10 to the negative 27th kilograms. Now, you may be tempted to say that the proton and the neutron have the same mass, but no, the mass of a neutron is greater than the mass of the proton. It's just only slightly greater, and we'd have to go out a couple more sig figs in order before we saw that. Now notice these are masses in kilograms, because that's the way that we roll in physics with kilograms. In chemistry, you probably encountered mass of these things in a different unit. Do you know what unit it was? Hopefully you're thinking to yourself, the AMU, atomic mass unit. I should have looked this up before this video, but I could write these in atomic mass units. I think I remember off the top of my head something like the proton is about 1.0, I think it's 0.0076 something or other atomic mass units, which is U, and the neutron is 1.0087 atomic mass units or something like that, and the electron is like 0.00 some other number atomic mass units, right? But like that's on the order of the size of that. So we made that number of atomic mass units because these numbers are really obnoxious to deal with. So oftentimes we create new units on the scale of what is easy to deal with. All right, keep that in mind. So then the charge of these things, because we know they are charged objects. Well, when they were first discovered, remember that Coulomb, in his work in the 1820s, had figured out the charge of much larger objects. He didn't realize that those objects were charged because of electrons, protons, and neutrons, and we'll get back to that in a minute. And so he made this standard of charge, this really large amount of charge. He didn't know it was due to a large amount of these things. So when we finally found out these things, their charges end up being really, really, really small in comparison. In fact, the charge on an electron is negative 1.6 times 10 to the negative 19th coulombs. It's actually 1.60 if we're going to 3 sig figs. That's an incredibly small amount of charge, and it is indeed negative because we said that the electron is going to be our negatively charged particle. Now, what about the proton? Well, hopefully what you remember in chemistry is an ion is something where electrons and protons are out of balance. That's why the charge on a proton has the same amount or size of coulombs, but just opposite sign. And that's going to become important in just a couple of minutes, right? So there we go. And the charge on a neutron is 0. And so that's charge in number of coulombs. Now, there's another unit of charge. In the same way that we made AMUs to create charges that were on a nice human scale here of like, what's the charge on a proton? 1 something, rather than, 1.67 times 10 to the negative 27 kilograms. We've done the same thing with charge. So this is charge in coulombs, but there's another type of thing. We're going to define something that's called 1 elementary charge. And sorry about this notation, an electron, if we're saying this is an electron, that's 1e negative. 1 elementary charge is just 1 little e. So little e is its own thing without the subscript. A superscript has its own meaning. And 1 elementary charge is defined as 1.6 times 10 to the negative 19th coulombs. So an electron in elementary charges is negative 1e, and a proton is a charge of positive 1e, and this is, once again, 0. So just keep those things in mind. Now, here's a great thing. You don't have to memorize that, because if you go to your tables that I gave you earlier, you'll find a couple of really great things. Oh, look, 1 elementary charge is 1.6 times 10 to the negative 19 coulombs. A coulomb is this many elementary charges, is what we ended up finding out, right? 6.25 times 10 to the 18th elementary charges is the number of charges you need to get a coulomb of charge. And then down here, you see the masses of the electron, proton, and neutron to 3 sig figs. So you don't have to memorize the information. That information is given to you. So in that light then, what does it mean to be charged? Well, when an object is negative, what would it mean for an object to be negative then? Well, an object is negative if it has more electrons than protons, right? Or a nice easier way to say that, the number of electrons is greater than the number of protons, okay? Therefore, what does it mean for an object to be positive? Well, apparently that's that the number of electrons is less than the number of protons. I just want to keep phrasing like that just structurally to make it easier. And what does it mean for an object to be neutral then? An object that's neutral, the number of electrons is equal to the number of protons. Okay, so with that being said, we need to stop and think for a second. Here is a piece of plastic, right? My pen. I could charge this up if I needed to, but here's a piece of plastic. How many electrons does this piece of plastic have? And hopefully you start thinking about chemistry. You're like, oh my God, that's a lot. Oh, so what is a lot? Is that millions? Is that billions? And that's not even close, folks, because we know that if we start thinking about stuff like gram molecular mass, right, that we should be thinking that this thing has not just millions or billions or trillions, but moles worth of atoms. And those atoms are made up of protons and electrons, moles, 6.02 times 10 to the 23rd of them, right? And this thing probably has 10, 20 moles of particles in it. So we're talking an amazing amount of particles. So for an object to be negative, all that means is that there's some slight imbalance in charge, that somehow there's more electrons than protons. It doesn't have to be many more. Just as long as there's not equality there, it's negative, right? So when an object is negative, it's just that there's some sort of imbalance in the charge. So when we say an object is charged, what we really should say is that an object has a net charge. Because an object that's neutral still has charges in it. It's just that the number of electrons and the number of protons balance out, right? So a charged object has a net charge. It has an imbalance of electrons and protons. We also should at this state say that neutrality, when an object is neutral, that this is going to be the equilibrium state, that all systems are trying to get towards neutrality if they can, that equality between electrons and protons, right? But there's reasons why they might get imbalanced, but just then if they can, they'll go back to balance. So then, What does it mean to be negative? What does it mean to be positive? Well, the idea here is that an object starts out neutral. So for it to be negative then, to end up with more electrons than protons, one of two things has to happen. Either this object must have gained electrons from somewhere or lost protons to somewhere. For an object to be positive, either it lost electrons or it gained protons. Okay, right, and obviously this has an equal number. But I'm going to tell you, only one of these things is happening, right? Hopefully you know from your study of chemistry, when an object has become negative, it's not because it's lost protons, but it's because it's gained electrons. When an object has become positive, that means that it's lost electrons. So to be negative means to have an excess of electrons. To be positive means to have a lack of electrons. It's missing electrons. Well, why is that true? There are three independent verifications that we can have for why that's true. So I'm just going to make a statement here, and I'm going to say that electrons are the mobile unit of charge transport generally. I don't want to say that there aren't times when I can have positive ions floating around, but in general, when we're talking about charge transfer, we're talking about electrons. And there's three reasons for it, okay? The first, very simple. Where are electrons compared to protons, right? Electrons are on the outside, protons in the nucleus. So which is easier to move around? Well, the electrons on the outside are easier to move around than the protons in the nucleus. Electrons are bound to that atom in a different way, in a weaker way, than the protons are bound inside the nucleus. The second argument might say is, well, oh, look at that. The mass of a proton is like it's like thousands of times bigger than the mass of an electron, right? Let's say just ballpark it's about 2,000 times the mass of an electron. It's actually not 2,000 times, it's a little less than that, but still. So if I want to make something charged, so I can either move an electron or move something that's 2,000 times more massive. That's like, oh, carry your book across the room or carry your Buick across the room. Which of those two things is going to happen? Well, I want to do the least amount of work to cause the same change. I'm going to move the less massive one. Now, the most important reason that we know that this is true, protons, what do I know about protons from chemistry? Oh, say for example, carbon. A normal carbon atom, carbon 12, right? Well, why is it carbon? Well, it's carbon because it has 6 protons. This piece of rubber here is largely made out of rubber. If I take this and I rub it with fur, and I can't seem to see where my fur is, right? And I charge it, it's not because, charge it negative, it's not because I'm stripping protons off of it, because I strip protons off of carbon, what do I get? I get boron. Boron has 5 protons, right? So we're not doing transmutation of elements. We're not doing alchemy here, folks. So the identity of elements doesn't change during charging process. And that's how I know that it's going to be electrons that are going to be moving around. So what is a charging process then? A charging process then is going to be anything. So a charging process is going to be anything where the number of electrons on an object changes. Either electrons are transferred off or onto that object. That's what it's going to mean for something to become charged. All right. So with that being said then, let's talk about what happened in the video with the balloon in my hair. That's a charging process that's called charging by friction. I started with 2 neutral objects. I started with the balloon and my head, which apparently is more spherical than the balloon. and they both start out neutral. But then when I rubbed them together, the balloon ended up being negative and my hair ended up being positive. Well, what happened there? Well, for something to become negative, it must gain electrons. For something to become positive, it had to have lost electrons. So in this charging by friction process, there must have been a transfer of electrons from my head over to this object. Now, why did it go that way? Why did the opposite not happen? That's a chemistry question as well. Just to remind you of a concept called electronegativity. Some things just have a larger propensity to give up electrons. Some things have a larger propensity to take on excess electrons. Rubber has a high electronegativity. It's going to, when it interacts with things, try and steal electrons from other objects. Hair has a lower electronegativity, not that it's like electropositive or anything like that, like it's throwing away electrons. It just holds on to them in a different way. So that's what's happening there. But here's the thing. How negative does this balloon get? Well, because this is happening due to transfers of electrons, then that must mean for every electron that the hair loses, the balloon gains. So in a charging by friction process, the balloon only becomes as negative as the hair becomes positive. So what does that remind you of? Well, hopefully it reminds you of the notion of a conservation law. And here we're going to have a conservation of charge. And that's going to say, in a closed system, the net charge remains constant. So here, the net charge, Q, is equal to 0. Here, it's still equal to 0. So if this ended up with a charge of plus 5 coulombs, this must end up with a charge of negative 5 coulombs. Those are ridiculously large charges, by the way, but just for example. So what's happening here is that there's a transfer of electrons. One thing loses electrons, one thing gains electrons. So actually, I'm going to end this video now because it's gotten kind of long. And in the next video, we'll talk about quantification of a lot of these notions as well as Coulomb's law.